Chapter 3 starts taking a look at graphing some specific functions. We're going to look at how we can graph polynomials, reciprocals, and rational expressions. To set this up, though, starting with the most foundational graph is a polynomial graph. We're going to first talk a bit about the shape of a polynomial graph. Now, polynomials will look something like 3x to the 4th minus 2x cubed plus 5x squared minus 7x plus 1. Or it might be, negative 3x cubed plus 7x squared plus 2x minus 5. Another example might be negative 4x to the 8th plus 3x to the 7th plus 2x squared minus 9. These are all polynomials. I want to do one more example, though. How about we do 2x to the 5th minus 3x to the 4th plus 7x squared minus 4x plus 2, something like that. The way we gauge the shape of a polynomial is we are going to have to look at the leading or largest exponent. Leading, we call it leading because it usually comes first. The leading exponent, the largest exponent, and we want to know, is it even or odd, and if it's positive or negative. And based on that fact, it's going to take one of 4 different basic shapes. 1, 2, actually let's do it this way. 1, 2, 3, 4. And how we're going to label this is going across these top 2 graphs are going to represent even leading exponents. The bottom 2 graphs are going to represent odd leading exponents. And the left side are going to represent positive, and the right side are going to represent negative. So the first graph, looking at the leading coefficient, is a positive 3. Actually, I should probably be a little more specific. Positive and negative coefficients. And even or odd is talking about the exponents. Both parts tell us something. So first, 3x to the 4th has an even exponent. Even exponent. And the coefficient 3 is positive. So that graph, what it's going to do is positive coefficients with even exponents come in from the top left, and then they're going to wiggle around in the middle. And we'll talk about the wiggle in a minute. But then they're going to leave up to the top right. A good example of this is x squared. We've seen x squared, the quadratic. It goes in from the top left and out the top right. In green here, we've got negative 3x cubed. The x cubed being odd and the coefficient being negative is going to stick us in the bottom right example. An odd negative is going to come in from the top right, wiggle around, and then go out the bottom right. An example of this would be negative x cubed. Another example here, negative 4x to the 8th is the leading coefficient. X to the 8th is even, but the coefficient is negative. And so what this graph is going to do is be a flipped version of the positive even. It's going to come in from the bottom left, wiggle around for a while, and go out the bottom right. And as you might expect, the 2x to the 5th is going to be a flipped version of the other odd one. The 2x to the 5th is going to come in from the bottom, wiggle around, and go out to the top. You should know these four shapes, basically where it comes in and where it goes out based on if it's positive or negative coefficients, and if the exponent is even or odd. I might even label this. Positive and negative is talking about the coefficient, the number in front. Even or odd, that's talking about the exponent. So that's how we determine the shape of the polynomial graph. Once we know the shape, we need to decide how it's going to wiggle in the middle. And the way we determine how it wiggles in the middle is we look at some key points. Just like when we were graphing our fundamental graphs in Chapter 2, there are key points on these polynomial functions. Now in Chapter 2, they were always the same, 0, 0, 1, 1, and a negative 1, either positive or negative 1. Here they're going to be different. They're going to be based on two things, the Y-intercepts and the X intercepts. The way we find the Y-intercept is we make the other variable, make x equal to 0, and solve. The way we find the X-intercept is we make the other variable, y, equal to 0, and solve. And usually this means with the x we're going to have to factor to solve. And we're going to talk about some more factoring strategies as this unit progresses. So for example, if we're asked to graph f of x equals x plus 2 times x minus 3 times x plus 4 times x plus 1, we can find the y-intercept by making all the x's equal to 0. 0 plus 2 is 2, times 0 minus 3 is negative 3. 0 plus 4 is 4, times 0 plus 1 is 1. This gives us negative 6 times 4 is negative 24, is the y-intercept. The x-intercepts we get by making the whole thing equal to 0, and so we end up with x plus 2 equals 0, setting each factor equal to 0, x minus 3 equals 0, x plus 4 equals 0, and x plus 1 equals 0. And when I do that, I get x-intercepts of negative 2, positive 3, negative 4, and negative 1. What about the shape? We're going to multiply these x's together. When we do, we get x squared cubed fourth. And the numbers in front are always 1. 1 times 1 times 1 times 1 times 1 is 1. So we have a positive coefficient with an even exponent. Positive coefficient comes in from the top left, wiggles around, and goes out top right. So let's see if we can graph it. So our y-intercept is at negative 24, so I will just label down here negative 24, there it is. Doesn't have to be to scale. The x-intercepts are at negative 2, and 3, and negative 4, and negative 1. So we know the shape. It's going to come in from the top left. It's going to go through the first x-intercept, and then it has to bend back to the next x-intercept, bend back to the next intercept, come all the way down to the y-intercept, and back up. So this graph is going to look something like this. That's how we're going to graph our key points. Find the y-intercept, find the x-intercepts. Let's do one more example. let's graph f of x equals negative x minus 3 times x minus 1 times x minus 2. Again, the first key point is the y-intercept, where we make all the x's equal to 0. So we have negative times negative 3 times negative 1 times negative 2. 4 negatives, our answer is going to be positive. 3 times 1 times 2 is 6. The y-intercept is 6. To find the x-intercepts, we make the whole thing equal to 0, and because it's already factored, we can take the x minus 3 factor and make it equal to 0, x minus 1 and make it equal to 0, and x minus 2 and make it equal to 0. And so when we solve, our x-intercepts are 3, 1, and 2. For our shape, we have a negative out front times x times x times x is going to be negative x cubed. Negative x cubed, that's an odd exponent with a negative leading coefficient, so it's going to come down, wiggle, and go back out, down. So when we try and graph this, our y-intercept is at 6. 1, 2, 3, 4, 5, 6. Our x-intercepts are at 3, 1, and 2. And so we know the graph is going to come in from the top left, go through the first x-intercept, through the next x-intercept, and through the next x-intercept, and out. And this is our graph. And that's basically all there is to graphing a polynomial. When you find your intercepts, you just go through all the intercepts and wiggle around, following the shape that we would expect based on the exponents, and we get our solution. There are a couple special factors, though, I want to make sure we're aware of that do slightly different but very similar things. Two that I want to be aware of. If we have x minus a squared, or really any even exponent, the graph of this is going to do one of two things. So let's say a, that 0 is right here. When we see x minus a squared is going to hit that point twice. So it goes through it once and comes out again. It's going to bounce back down. It's coming in from the top, hits it, and bounce back for the squared. Even exponents will bounce, just like x squared does, on the x-axis. Instead of going through, it's going to bounce. Another one similar to that, if I have x minus a cubed, or really this works for any odd exponent, depending on which direction we're coming in from. Again, a is the 0. If we're coming in from the bottom, the cubed is actually going to make it level out and flatten. So instead of just going straight through, depending on which direction we're coming from, it's going to level out and flatten and then continue on through. So an example of this happening would be if f of x equals x minus 1 cubed times x plus 2 squared. The y-intercept is still very much the same. We have negative 1 cubed times 2 squared when we make all the x's equal to 0, and that comes out to negative 4. The x-intercepts, again the same way, we make it equal to 0, so x minus 1 equals 0, or x plus 2 equals 0. And so our x-intercepts are 1 and negative 2. For our shape, we've got x cubed And x squared, that's a total of x to the 5th. X to the 5th, it's positive. It's going to come in from the bottom, wiggle around, and go out the top. So let's see if that's what we get. Our Y-intercept was at -4. Our X intercepts were at 1 and -2. But the one at 1 was cubed, right? I'm going to put a little 3 next to it so I know it's cubed. And the one at -2 was squared. I'm going to put a 2 next to it so I know it's squared. Because what's going to happen is as the graph comes in from the bottom, because it's a positive 5th power, and it hits that squared, it's going to bounce back. Then it's going to come up and it's going to approach the cube, and it's going to level off because it's a cubic. Again, instead of going straight through, it leveled off at the cube. Instead of going through, it bounced at the square. That's the way we're going to have to handle those special factors. Let's do one more example. Let's do, what number am I on? 2. Let's do f of x equals x plus 3 squared times x minus 4 squared times x plus 1 cubed times x minus 1. Again, we're going to start with the y-intercept, making all the x's equal to 0. So we have 3 squared times -4 squared times 1 cubed times -1. 3 squared is 9, times -4 squared is 16. Be careful putting that negative in parentheses. Times 1 cubed times -1, that's going to be 144 negative. We then can find the x-intercept by taking each factor, making it equal to 0. X plus 3 equals 0. X minus 4 equals 0. X plus 1 equals 0. X minus 1 equals 0. You probably don't even have to write this step because you can see x is equal to -3, 4, -1, and 1. Shape-wise, we can kind of look at the squaring of the x's and the cubing of the x's. So we've got 2, 4, 5, 6, 7, 8 x's, x to the 8th, all multiplied together. The leading term is going to be a positive 1. So it's positive with an even exponent. It's going to come in from the top, wiggle, and go out the top. So let's see what this graph looks like. Y-intercept is at -144. That's down here somewhere. The x-intercepts are at -3, 4, -1, and 1. But again, I want to notice that some of these exponents, some of these intercepts had exponents on them. The -3 was squared. So we'd expect that one to bounce. I'll put a 2 for squared. The 4 was squared also. Put a 2 there on the 4. The -1 was cubed. So when we come in from the top left like we expect, when we hit our first one at -3, we should bounce. That's a squared. The next one's a cubic. It should level off. And then go down all the way to -144. Come back up at the 1. It's just a first power, so it's just going to go through. No leveling off, no bouncing. But this time when we hit the 2, we're going to bounce off the 2 and go out the top. And we have our graph. So you should be able to take any graph in factored form, any polynomial, and quickly sketch more or less what the graph looks like, knowing where it comes in, where it goes out, what the x-intercepts are, and what the y-intercepts are. Knowing when to go through an intercept, when to bounce, and when to level off. We can also do the same exact process backwards. I can give you the graph and ask you to give me the equation. And again, the information that we're interested in is the same information, the intercepts, which are going to derive our entire result. Let's start with a simple example. Let's take a graph that comes in, goes through this point, bends back, goes through that point, and bends back and goes through that point. The y-intercept, you see, is at 1. We're going to come back to the y-intercept. What's going to be interesting to us as we start to build the equation that this graph goes with is we start with the x-intercepts. X equals -2, x equals -1, and x equals +1. Remember, those x-intercepts came off of finding our factors that were equal to 0. So we want to make these equations equal 0. The first one we add 2, and we get x plus 2 equals 0. That's one of our factors. The next one we add 1, and we get x plus 1 equals 0. There's another factor. The next one we subtract 1, and we get x minus 1 equals 0. And so we use those factors of x plus 2 times x plus 1 times x minus 1 to start to build our polynomials. Now there's a little bit of a catch. We can't just say y equals and be done, because we haven't yet used the y-intercept. There could be, and in fact most of the time there is, some number, we're going to call it a, in front of all these factors. And the only way to find that a is to use another point on the graph, usually the y-intercept. So here the y-intercept is 1, so y equals 1 when x is equal to 0. We don't know what a is, but if x is 0, we have times 2 times 1 times -1. Or cleaning it up, -2a is equal to 1. Solving for a is quite simple. We divide by the -2, and a must be -1/2. And so we can see then our entire function is y equals that a, the -1/2, times x plus 2, times x plus 1, times x minus 1. We now have our polynomial. Let's do another example that's probably a little more interesting to this to wrap up. So if we call that example 1, this next one we're going to call example 2. So this one's going to come in, we're going to bounce, come up, go through, come up, and then we're going to level off as we go through there. And we're going to come up with the equation, the function, for this graph. Well, you'll notice the first is the y-intercept is at 2, but remember we're going to care more about that at the end when we try and figure out what a is. The x-intercepts, we've got an x-intercept at -1. But notice it bounced. Because it bounced at that point, what's going to be special about this factor? This factor is going to be squared. So when we add 1 to both sides, we get x plus 1 equals 0, but that factor should be squared to create the bounce. The next x-intercept is at x equals 1. It just goes through that point, so we'll subtract 1. Nothing fancy, x minus 1 is our next factor. Our third x-intercept at x equals 4, though, is interesting because you notice the graph levels off. It doesn't just go through it like the intercept in the middle did. Because it levels off, we know we're probably going to need to cube this factor. So when we subtract 4 and say it equals 0, we also need to make sure that factor is cubed to give us that illusion of leveling off. So the first is x plus 1 squared, then we had an x minus 1, and then we had our x minus 4 cubed. And again, we'll say y equals a times all of that, because we need to figure out if there's a number in front. Usually there is, and we can calculate that from our y-intercept. Our y-intercept is 2, so we'll say 2 equals, and we'll make all the x's equal to 0. So we have a times 1 squared times negative 1 times negative 4 cubed. So 2 equals, 1 squared is 1, negative 4 cubed is negative 64, times negative 1 is positive 64a. Divide both sides by 64, and a is 1 over 32. So our final function, this graph that we have drawn in front of us here, is 1 over 32 times x plus 1 squared times x minus 1 times x minus 4 cubed. Again, on today's assignment, we're just getting that basic pattern of what these polynomial graphs look like. You should be able to find the y-intercept. You should be able to find the x-intercept and decide, is it going to go through it? Is it going to bounce because of an even exponent? Or is it going to level off because of an odd exponent? In addition, you should know the general shape of every polynomial based on if it's even or odd exponents and whether the coefficient is positive or negative. You should know where it comes in and where it goes out. Take a look at the homework and practice a few of these. These are really easy and go fast once you get it. Takes a little bit to get it, though, but once you get that pattern down, every problem essentially the same. So good luck on the homework. We will see you in class tomorrow. Synthetic division. This is going to be a day where we look at a nice trick that when it works mathematically, it's going to save us a lot of time and a lot of work. We're going to come up pretty soon to a situation where we're going to have to do a lot of long division, and that's going to slow us down. Synthetic division is going to be the shortcut that makes life a lot nicer for us. But before we get into division, I want to talk a bit about substitution. And the idea here is if I've got something like f of x equals 3x cubed minus 2x squared minus x minus 15. And we wanted to find maybe what f of 2 equals. Well, the way we've done this up till this point is we put 2 in for all the variables. So it would be 3 times stuff cubed minus 2 times stuff minus stuff, 2 times stuff squared, minus stuff minus 15. And we'd plug the 2 in there all the way across. So then exponents first, we would do 2 cubed, which is 8, minus 2 times 2 squared, which is 4, minus 2 minus 15. 3 times 8 is 24, minus 8 minus 2 minus 15. And then just going across, 24 minus 8 is 16, minus 2 is 14 minus 15 is negative 1. And that's not too bad to do, but I want to show you kind of a neat little trick that we can do to make this substitution easier. It's called synthetic substitution. What I do is I put a little box over here on the side where I'm going to stick the number that we want to substitute in. We're going to substitute in a 2, and I'm going to draw a line here, leaving 2 lines of space above, and I'm going to put the coefficients of this problem all the way across. So it's 3, negative 2, negative 1, and negative 15. Okay? There's the setup. What we're going to start doing now is that we're going to bring this 3 straight down. And then we're going to take the 2 and we're going to multiply by what's in the bottom row. 2 times 3 is 6. And I'm going to stick that up here underneath the negative 2. Now what I'm going to want to do is I'm going to add my column straight down. Negative 2 plus 6 is 4. And then we repeat this process. We're going to multiply. 2 times the 4 is 8. And when we add, negative 1 plus 8 is 7. And then we multiply 2 times the 7, we get 14. And when we add negative 15 plus 14, we get negative 1. And what I want to notice is this last number we ended up with is the same number that we ended up with when we plugged in the 2. This process was probably much easier to work with, especially if we were doing a problem such as f of x equals 7x to the 5th plus 2x to the 4th minus 38x cubed minus 95x squared plus 6x minus 9. And we're going to be asked to find what f of 3 is. I really don't want to plug 3 into this long thing and work it out. It is going to be a pain. But what we can do is synthetically substitute the 3 into the problem, taking the coefficients all the way down the line. When we do, we have 7, 2, negative 38, negative 95, 6, and negative 9. Bring the 7 straight down, and then go through the process again. 7 times 3 is 21, plus 2 is 23. Multiplying by 3, 23 times 3 is 69. Minus 38 is 31. Times 3 is 93. Subtracting the 95, we get negative 2. Times 3 is negative 6. Subtracting the 6, we get 0. Times 3 is 0, which brings it down to a negative 9. If we were to plug 3 into this long thing and do all the algebra arithmetic to work it out, we'd end up with negative 9. But the synthetic division made the problem much quicker for us and quite easy to handle. I'm sorry, synthetic substitution. Substitution is what we're doing here. Let's do another problem. How about this? Let's say f of x equals 3x to the 4th minus 2x squared plus 5. And we're going to find f of negative 2 this time. Before we get too far into this problem, I want to notice something that's different about this problem. This problem is missing x cubed. There's no x cubed term. It's also actually missing the x term. Anytime something is missing, we need to add 0 of it. So we're going to add 0x cubed, and we're going to add 0x to this problem as we set up the synthetic substitution. If you don't add the zeros, it will not work. So we've got the negative 2 outside, a 3, 0x cubed, negative 2x squared, 0x, and 5. Bring 3 straight down. 3 times negative 2 is negative 6. Negative 6 plus 0 is negative 6. Times 2 is 12. Minus 2 is 10. Times negative 2 is negative 20. Plus 0 is negative 20. Times negative 2 is positive 40. Plus 5 is 45. And that quick we have come up with our answer that f of negative 2 is equal to 45. So that's an important step. We don't want to forget it. It's going to catch people unaware. If you are missing a term, you need to add 0 of it for the synthetic substitution to work. It should count down. 4th power, 3rd power, 2nd power, 1st power, 0 power. It should count down. If one is missing, it won't work. Let's try another one. Let's say f of x equals x to the 4th minus 5x cubed minus 7x squared plus 29x plus 30. And we're going to find f of 5. So we stick 5 in the corner, and the coefficients are 1, negative 5, negative 7, 29, and 30. Bring the 1 down. Times 5 is 5. Minus 5 is 0. Times 5 is 0. Minus 7 is negative 7. Times 5 is negative 35. Plus 29 is 6. Negative. Times 5 is negative 30. Plus 30 is 0. So f of 5 is 0. However, this is interesting, and I want to plant here and look at this. F of 5 is 0. That means when x is equal to 5, we have a y value of 0 or an X intercept. What this also means, if I subtract 5 from both sides of this x equals 5, x minus 5 is a factor. We should be able to factor x minus 5 out of this big thing. This big thing is x minus 5 times something. Well, let's find out what that something is. The way we get something out of there is we use long division. And you remember doing long division. We take x minus 5 and we divide it into the entire polynomial, which was, I scrolled off too fast, x to the 4th minus 5x cubed minus 7x squared plus 29x plus 30. So if we divide it out, x goes into the x to the 4th, x cubed times, we'll say 1x cubed times. Multiplying 1x cubed times x minus 5, we get x to the 4th minus 5x cubed. Changing the signs so that we can combine, we get 0. Bring down negative 7x squared. X goes into 0x cubes, 0x cubed times. Multiplying by 0 is not going to do anything, so let's just move down the next term. Plus 29x. X goes into negative 7x squared, negative 7x times. Multiplying out front, we got negative 7x squared minus 35x. Change the signs so that we can combine. Oop, I'm sorry, negative 7 times negative 5 should have been a positive 35. So when we change the sign, we get 29 minus 35x, which is negative 6x. Bring down the plus 30. X goes into negative 6x, negative 6 times. So we've got negative 6x plus 30. Change the signs, and we get 0. So we've got our solution. But what's interesting to look at here is when we had 1x cubed, that corresponded with the 1 from the synthetic substitution. The 0x, that should have been squared. Boy, I really did this wrong. The 0x squared corresponds with the 0 in the synthetic substitution. The negative 7x corresponds with the negative 7 in the substitution. The negative 6 corresponds with the negative 6. And the remainder corresponds with the solution, or the remainder. What this means is essentially substituting in 5 is the same as dividing out x minus 5. That means our synthetic substitution could also be thought of as synthetic division. Where we are going to divide out the 0. In other words, if I'm asked to find 2x cubed minus 20x squared plus 56x minus 46, and we're going to divide out x minus 6, we just need to identify the 0 that's being divided out. Make the denominator equal to 0, add 6 to both sides. That's the number that goes in the corner. We'll put the 6 in the corner and we get 2, negative 20, 56, and negative 46 for our numbers across. And this becomes our synthetic division. Bring the 2 down. 2 times 6 is 12, minus 20 is negative 8, times 6 is negative 48. Add 50 is 2, times 6 is 12, minus 46 is negative 34. To get the variables in there, we're going to drop 1 off of the x cubed, the leading coefficient. So we have x squared, x, and a constant, and the last part is the remainder. We can either say this is a remainder of negative 34, or we put the negative 34 over the denominator of x minus 6. So to clean it up, when we divide, what we get is 2x squared minus 8x plus 2 minus, because the remainder was negative, 34 over our common denominator of x minus 6. We have synthetically divided out the x minus 6. I love this method because it is so much easier than long division. Let's try another one. Let's try 2x to the 4th plus 5x squared minus 7x plus 1. And we're going to divide it, whoops, wrong color. We're going to divide it by x plus 2. To set it up, we find the 0. X plus 2 equals 0, so x equals negative 2. That's who's going in the corner. We want to be careful as we go across, though. Don't get moving too fast. You might notice we're missing the 0x cubed. Always check to see if anybody's missing. So we're going to go across. We're going to need 2. Don't forget the 0 for the x cubed, then the 5 for the x squared, the negative 7, and the 1. Don't forget the 0. Don't put it in the wrong spot. It must count down 4, 3, 2, 1, 0. Alright, so we've got 2 times negative 2 is negative 4, plus 0 is negative 4, times negative 2 is 8, plus 5 is 13, times negative 2 is negative 26, minus 7 is negative 33, times negative 2 is positive 66, and so we end up with 67. Drop the exponent by 1, so we're going to start with x cubed, x squared, x, a number followed by the remainder, which is going to go over our denominator, x plus 2. So for our final answer, 2x cubed minus 4x squared plus 13x minus 33. This time the remainder is positive, so we will add 67 over x plus 2. Let's try one more. It's going to be a lot of fun because it's going to involve fractions. Number 3, we have 3x cubed minus 4x squared plus 5, and we're going to divide by 2x minus 3. We make that equal to 0 to find our 0 that's coming out. So we add 3 and divide by 2, 3/2. So we're going to see if 3/2 can come out. Again, did you check? Do the exponents count down? 3, 2, we're missing 0x. So we've got 3, negative 4, 0, don't miss the 0, 5. Bring the 3 down. And now we have to deal with fractions, but the idea is the same. Remember, that's 3 over 1, so 3 times 3/2 is 9/2. To add, we'll make the 4 have a common denominator. It's going to be negative 8/2. So negative 8 plus 9 is 1/2. Times 3/2 is going to be 3/4. 3/4 plus 0 is just 3/4. That's nice. 3/4 times 3/2 is going to be 9/8. Multiplying across, which means the 5 is going to be 48. So 9 plus 40 is 49 over 8. And again, we drop 1 down from the exponent, so we're x squared, x, and then a remainder, which is going to go over the 2x minus 3. So we have 3x squared plus 1/2 x plus 3/4 plus, because the remainder is positive and that 8 is part of the denominator, if we multiply by the reciprocal, we'll end up with 49 over 8 times 2x minus 3. And that's what we get when we do our synthetic division. Synthetic division is a real simple process, but you need to practice synthetic division. Just getting synthetic division is not going to be enough. You want to practice it so that you can run through this process fast, fast, fast. Because what we're going to do in tomorrow's lesson is we are going to be doing lots of synthetic division to solve one problem. You don't want to get bogged down on the synthetic division. You need to be fast, fast, fast at this process. You need to know what step comes next without hesitating and be able to run through it fast so that you can focus on tomorrow's lesson, which is called the rational root theorem. Practice today. We'll see you tomorrow in class. Thank you. Section 3.3 takes a look at what I think is one of the neatest theorems in all of precalculus, and that's the rational root theorem. And basically what this is, this rational root theorem, is a way to help us factor polynomials that are 5th, 6th, 7th, 8th power quite quickly, almost in a way that guides our guess and check to find all the rational roots of a polynomial. Now, rational roots means the answer is a fraction. We can set that factor equal to 0 and we'll get a fraction for our answer. Might be a whole number too. The idea is if f of x is equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub n minus 2 x to the n minus 2, and so on and so on and so on, all the way to a sub 1 x to the first plus a sub 0. Basically any type of polynomial, 5x to the fifth plus 2x to the fourth plus 7x to the third plus 6x squared plus 2x plus 9. Any type of polynomials. Then all rational roots are of the form p sub I divided by q sub I, where p sub I is a factor of a sub 0 and q sub I is a factor of a sub n. In other words, all the factors of the last term should be considered for the numerator, and the variant factors of the first term, the coefficient at least, should be considered for the denominator. It's probably easier to see what's happening when we look at a couple examples, and so we're just going to do 3 examples today. The first example, we're going to try and factor 6x cubed plus 13x squared minus 19x minus 12. And in order to factor this, we're going to identify our p's are always going to be the last term. P is 12. And so we list the factors, I should label it clearly, the factors of p, or the factors of 12. Well, 12 is divisible by 1, 2, 3, 4, 6, and 12. It's all the factors that divide into 12. Q is the first number, which is 6. So then we will consider the factors of 6. Well, the factors of 6 are 1, 2, 3, and 6. The way we figure out our possible roots, rational roots at least, is we take all the top line and put them over all the bottom line. So in other words, first the bottom is 1, so we're going to take the entire top line, all those blue numbers, and put them over 1. So we've got 1 over 1, 2 over 1, 3 over 1, 4 over 1, 6 over 1, and 12 over 1. Then we put them all over 2. 1 over 2, 2 over 2, 3 over 2, 4 over 2, 6 over 2, and 12 over 2. Then we put them all over 3. 1 over 3, 2 over 3, 3 over 3, 4 over 3, 6 over 3, 12 over 3. Then we put them all over 6. 1 over 6, 2 over 6, 3 over 6, 4 over 6, 6 over 6, and 12 over 6. When we reduce these, we're going to get a lot of repeats and a much simpler list to work with. So 1 over 1 reduces to 1, 2 over 1 reduces to 2, 3 over 1 to 3, 4 over 1 to 4, 6 over 1 to 6, and 12 over 1 to 12. The rest are all going to be our fractions. 1/2. 2 over 2 reduces to 1. That's already in our list, so we're not going to repeat it. 3 over 2. 4 over 2 reduces to 2, which we already have, so we're not going to repeat it. 6 over 2 reduces to 3, we have that. 12 over 2 reduces to 6, we have that. 1/3, that's a new one. 2/3, that's a new one. 3/3, that reduces to 1, we have that. 4/3, 6/3 reduces to 2, we have that. 12/3 reduces to 4, we have that. Then there's 1/6, 2/6, which reduces to 1/3, we have that. 3/6 reduces to 1/2, we have that. 4/6 reduces to 2/3, we have that. 6/6 reduces to 1, and 12/6 reduces to 2. So we'll cross that one out also. So we've got this new list, and it looks like a long list, but it is a list of the only possible rational roots to our original problem. 1, 2, 3, 4, 6, 12, 1/2, 3/2, 1/3, 2/3, 4/3, and 1/6. And because this is a third power, 3 of those probably work. We just don't know which 3. This is why we learned synthetic division yesterday. We're basically going to use synthetic division to factor out each of these roots as fast as we can to hopefully find somebody who works. So we'll just start working down our list, starting with 1, and we've got coefficients of 6, 13, negative 19, and negative 12. Well, the 6 comes down. 6 times 1 is 6. 6 and 13 is 19. Times 1 is 19. 0, 0, negative 12. We're looking for a remainder of 0 if it's a real root. 12 did not work, so 1 is out. So we try another number. We got to try both the positives and the negatives of each of these rational roots. So we're going to try negative 1. So let's do 6, 13, negative 19, negative 12. 6 times 1 is negative 6. 7 times negative 1 is negative 7. And that's going to give us negative 26 and 10, 26. And you can tell this is not going to give us 0. So 1's out. Going to take up a lot of space, but we've got our list of roots here. Let's try 2. Coefficients were 6, 13, negative 19, negative 12. 6 times 2 is 12, plus 13 is 25, times 2 is 50, minus 19 is 31, times 2 is 62. That's definitely not going to give us 0 at the end. So that one's out. 2 doesn't work. We'll try negative 2. 6, 13, negative 19, negative 12. Bring down the 6. Times 2 is negative 12. 1 times negative 2 is negative 2, which gives us negative 21. Times negative 2 is 42. That's not going to give us 0 either. So 2 and negative 2 both don't work. They are out. Let's try 3. 6, 13, negative 19, negative 12. 6 times 3 is 18. 18 and 13 is 31. Times 3 is 93. 93 minus 19. You can tell this number is just way too big. Once you get a feeling that the number is getting way too big, we can cross it out as well. So now we try negative 3 with 6, 13, negative 19, and negative 12. 6 comes down. 6 times negative 3 is negative 18. Gives us negative 5 times 3 is 15. 15 and negative 19 is negative 4. Times 3 is 12. And look at that. We got our 0 that we were looking for. We have a winner. X equals negative 3 is a factor, or is a solution. To get the factor, we have to add 3 to both sides to make it equal to 0, right? X minus 3 equals 0. So x minus 3 is a factor of our original problem. What's left becomes the remaining factor, and if you remember, we started with x cubed, so we will do x squared, x, and minus 4, so we have 6x squared minus 5x minus 4. And now that it's a quadratic, we can factor it using that guess and check method that we are so familiar with now. 6 is probably 2x times 3x. 4 might be 2 and 2, but that would be putting a 2 with a 2x, and there's no GCFs allowed. So it must be 4 and 1, and 4 can't be with the 2, because that would have a GCF as well. So I'm looking at negative 4, positive 1 will give us that negative 5 in the middle. And we have now factored our original polynomial. X plus 3, 2x plus 1, 3x minus 4. Notice the other roots, if we had solved them. The roots would be 3, negative 1/2, and 4/3. And those are all on our list. 3, 1/2, and 4/3. So as we had gotten to those would have worked and the others would not have. So this process, it's going to be the exact same process for every single problem. It's really a educated guess and check process almost. Don't spend time trying to find the correct answer the first time. Start using synthetic division and just start pulling out your possibilities. First, we started with our factors of the last term, factors of 12. Then we considered factors of the first term, factors of 6. And that allowed us to make all of our possible roots by making fractions out of those. P over Q, P over Q, P over all the Q's, P over all the Q's. Reducing those just gave us a nicer list that we could work with, and then came the synthetic division until we stumbled upon one that worked. Every problem is the same. These just take some brute force to work out. Some of them get big and ugly. Some of them aren't so bad. Let's try and factor x to the 4th minus x cubed minus 3x squared plus 5x minus 2. 2 is our p. That's nice. It only has factors of 1 and 2. Our q, that's the front number of 1, and that's really nice. It's only got a factor of 1. So for our roots, PQR, P's, Q's, and roots, it's going to be the P's over all the Q's, or 1 over 1 and 2 over 1, which will reduce to 1 and 2. Only possibilities here, 1 and 2. Maybe negative 1 and negative 2. Some people like to label those plus and minus, so they don't forget. Positive 1, negative 1. Positive 2, negative 2. So let's start with the positive 1. We got 1x to the 4th, negative 1x cubed, negative 3x squared, 5x, and negative 2. Bring down the 1. 1 times 1 is 1. Brings down a 0. 1 times 0 is 0. Negative 3 times 1 is negative 3. Plus 5 is 2 times 1 is 2. And look at that. It worked out to a 0 our very first time. This means x equals 1 is one of our solutions. Subtract 1 from both sides, and we have x minus 1 equals 0. X minus 1 is a factor. So essentially we have x minus 1 times the stuff that's left, x cubed plus 0x squared minus 3x plus 2. But we still have a cube. So we still need to keep working on it. We're going to pull out another root. We want to get down to a quadratic with just x squared so that we can use just our normal factoring methods. So we've got the x minus 1. We need another one. We can even just work right underneath if we wanted to. But when we do, use the smaller fewer numbers. Don't go back to the original looking for more factors, because that's more work. We've now reduced it down to 1, 0, negative 3, 2. So let's go from there. Another thing to note is we need to still test 1. There might be more than a single 1 as an option. So we're going to test 1 again. So bring down the 1. 1 times 1 is 1. Plus 0 is 1. Times 1 is 1. Minus 3 is negative 2. Times 1 is negative 2. Comes out to a 0. Notice the 1 worked again. That means x equals 1 is another solution. So if we subtract 1, x minus 1 is another factor. So we have the original x minus 1, our new x minus 1, and what's left is 1x squared plus 1x minus 2, pulling that from the bottom row. And now that that's just x squared, we can factor that using the methods we're more familiar with. X squared is x times x, and 1 times 2. To get the negative 2, we need a positive 2 and a negative 1, so that's going to be x minus 1 cubed times x plus 2. And the advantage of the cube is it's going to help us as we try and graph this polynomial. We can see that the zeros are at 1 and negative 2, but the 1 was a cubic. So 1 and negative 2, the 1 was a cubic. The original problem was a positive x to the 4th, so we know it comes down from the top right. As it comes towards the 1, because it's a cubic, it's going to level off, not just go through it and go up. And we're able to graph our polynomial. This is x to the 4th minus x cubed minus 3x squared plus 5x minus 2. So the big thing we learned in this example is once we have found a 0, if we're going to still look, use the abbreviated, simpler form. Use those numbers that we just found, not the original numbers. It's going to be easier. Another thing we learned is make sure just because 1 came out, we still have to test 1 again. We have to test every root until it fails. We saw a lot of failing in the first example. Once they failed, we cross them out. But don't cross them out until they fail. If they succeed, they might be successful again. Let's do one last example. 12x cubed plus 8x squared minus 3x minus 2. We're going to factor, and if we have time, we'll graph it as well. P's come from the end. 2 is nice. It's only divisible by 1 and 2. Q's come from the beginning. 12 has a few factors. It's divisible by 1, 2, 3, 4, 6, and 12. And so for our possible roots, we put the 1 over all the Q's, and the 2 over all the Q's. So first we put them over 1, 1 over 1, 2 over 1. Then put them over 2, 1 over 2, 2 over 2. Put them over 3, 1 over 3, 2 over 3. Put them over 4, 1 over 4, 2 over 4. Put them over 6, 1 over 6, 2 over 6. Put them over 12, 1 over 12, 2 over 12. Now we can go through and reduce, and as we do, we'll get rid of our repeats. 1, 2, 1/2, 2 over 2 reduces to 1. We've already got that. 1/3, 2/3, 1/4. 2/4 reduces to 1/2. We have that already. 1/6. 2/6 reduces to 1/3. We have that already. 1/12. And 2/12 reduces to 1/6. We have that already. So now to find our correct roots, just have to start working through.
start with our 1. Coefficients are 12, 8, negative 3, and negative 2. Bring down the 12. Times 1 is 12, plus 8 is 20, times 1 is 20, minus 3 is negative 17, and you can see this is not going to give us a 0. So let's try negative 1 with 12, 8, negative 3, negative 2. Bring down the 12. Times negative 1 is negative 12, plus 8 is negative 4, times negative 1 is positive 4, plus negative 3 is 1, times negative 1 is negative 1. Not quite. Not going to work for us. So the 1's out. We tried the plus and minus. Don't forget, very important, you got to try plus and minus all the way through, positive and negative on each one of these. Checking both. So 1 didn't work. We're going to try 2 with 12, 8, negative 3, and negative 2. 12 times 2 is 24, plus 8 is 32, times 2 is 64. I can see already these numbers are getting huge. Probably not going to work. Let's try negative 2. With 12, 8, negative 3, and negative 2. Bring down the 12. Times negative 2 is negative 24, plus 8 is going to be negative 16, times negative 2 is 32. Again, it's getting huge. It's not going to go away. So the 2's are out. Now we get to the fractions, and really there's no best fraction to try. You might think, hey, I feel like we do better with the negative, so maybe I'm going to try negative 1/2 first. Let's see, with 12, 8, negative 3, and negative 2. 12 times 1/2 is negative 6, plus 8 is 2, negative 1/2 is negative 1, which gives us negative 4. Negative 1/2 gives us 2. Negative 2 and 2 gives us 0. And look at that, we've got our 0. So since we have a solution, we say x equals that solution. X equals negative 1/2. So if we add the 1/2 to both sides, we get x plus 1/2 equals 0. And x plus 1/2 is a factor then. What's left becomes the 12x squared plus 2x minus 4. Checking for a GCF first, we can pull a 2 out of there. 2 times x plus 1/2. Times 6x squared plus 1x minus 2. And 6x squared is probably 2x times 3x. The 2 is probably 2 times 1, and we can't put the 2 with the 2. No GCFs allowed. So if we do a positive 2 and a negative 1, that's going to give us that in what we want in the middle. Another thing I notice is distributing the 2 through the parentheses is really nice because it's going to clear that fraction. So that's what I'm going to do. I'm going to do 2x plus half 2 is 1. And now it is completely factored. 2x plus 1, 2x minus 1, 3x plus 2. We can even graph this because we know our solutions are negative 1/2, positive 1/2, and negative 2/3. And so if we were to graph it, there's 1, negative 1/2, positive 1/2, and negative 2/3 is going to be right there. Going back to the beginning, it was a cubic, so it's going to come in from the bottom. Went too far. It's going to come in from the bottom, wiggle, and go out the top. The Y-intercept, when you figure it out, turns out to be negative 2. So that's the rational root theorem. It's a big plug-and-chug system, but it works every time. It'll find you your factors. What we're going to do is we're going to identify our P and our Q and all of those factors. use that to come up with all of our possible roots and reduce them. And then lots of synthetic division to see which ones work and which ones don't. Take a look at the homework and practice, practice, practice these, and come to class with questions.
Section 3.4 starts taking a look at how we can graph reciprocal functions. And reciprocal functions are real nice to graph. The reciprocal part is easy as long as you can graph the denominator part. And it's all based on this idea, what we're going to call the big-little principle. And the idea behind the big-little principle is if I take a big number like 1,000, and I flip it over and look at its reciprocal 1 over 1,000, the reciprocal of the big number has become a little number. Similarly, if I took maybe 1 over 1,000,000, a really little number, if I flip over a really little number, I get 1,000,000. The reciprocal of a small number is a big number, and the reciprocal of a big number is a small number. That's the big-little principle, is that the reciprocal of a big number is small, and the reciprocal of a small number is big. And this can even stretch out to another special case that I want to take a look at, and that is the reciprocal of 0. 0 is the smallest number we can get. And so its reciprocal should be as large as we can get. And 1 over 0 is technically undefined. So what we're going to do is we're going to say it's basically infinity, or a vertical asymptote. So if you see a vertical asymptote or a 0, they're actually going to be reciprocals of each other. So anytime we see an asymptote, the reciprocal of that asymptote is going to be 0. The only other big thing we want to know about reciprocals in this big-little principle is reciprocals of negatives are still negative. Reciprocals of positive if I can spell it, reciprocal of positives are positive. In other words, the sign's not going to change as we flip things over. So things above the x-axis are going to stay above the x-axis. Things below the x-axis are going to stay below the x-axis. Their size is going to change. Their distance is going to change from big to little or little to big. But reciprocals will keep the same sign. And what this basically means is if we are able to at least graph the denominator, we can use the reciprocal to graph, or the big-little principle, to graph the functions. Let's write that down. We're going to graph the denominator. Then we're going to, well, we'll do a middle step actually. We will identify key points. And with these key points, the x values are going to stay the same. It's the y values that we take the reciprocal of, 1 over the y value. And then we will use the big-little principle to fill in the rest of the information. So for example, if we wanted to graph f of x equals 1 over x plus 3, we did graph this back in Unit 2 using our translation rules and moving graphs around. But we can also graph it as a reciprocal of simply the x plus 3 function. And it's probably a little quicker. If we look just at the denominator, x plus 3, and we were to just graph the denominator, we would know that has a y-intercept of 3 and a slope of rise 1, run 1. So we should look something like this for our graph. And the key point on this graph really is the 0, 3, that y-intercept. So if we want to come over here, let's actually label this. That is actually the graph of x plus 3. We'll come over here to the side then, and we're going to do the graph of the reciprocal, the graph of 1 over x plus 3. First thing I'm going to look for is the key points. The first key point is 0, 3. We're going to graph the reciprocal of the y-coordinates. So it's still at 0. Now it's going to be 0, 1/3. The reciprocal of the y-coordinate. Next key points we're going to look for are any X intercepts or asymptotes. X intercept, the value is 0 there, and the reciprocal of 0 we said would be a vertical asymptote. So we're going to see an asymptote at -3 where there was a 0 before. Zeros turn into asymptotes. Asymptotes turn into zeros. Next, if we look to the left of the asymptote, we notice that we're negative and little to begin with. Close to the asymptote, we're negative and little. Far from the 0, we are negative and large. So we're going to follow that pattern on our graph. Close to the asymptote, the opposite of little is big. And then as we get farther and farther away, it should get littler and littler. Notice close, it was little. So close, we're far. At the edge, it's big. So our edge, we're little. Big, little principle. Go the opposite direction. We should, however, never cross the x-axis in our reciprocal graph, in this part of the reciprocal graph, because as you notice, we are always negative on the left. So the graph should always be negative on the left, because reciprocals do not have sign changes. However, on the right, you notice it's always positive, so the rest of the graph should always be positive. Notice we start close to the 0, so we should start far from the vertical asymptote. We end far from the x-axis, so we should end close to the x-axis, going through our key point. So big little principle says we start big, come down through our point, and get little. And this is going to now be the graph of our reciprocal function, 1 over x plus 3. Big becomes little, little becomes big. Some people like to graph these on top of each other rather than doing two graphs to help them see the big little principle play out. And if we do that, again, you'll see, I'm going to do pink for the reciprocal. We'd put an asymptote through the 0. 0, 3 would become 0, 1/3. And then where the graph is negative and large, we start negative and small and come in. So you can see the corresponding, when the blue gets close to the x-axis, the pink gets far from the x-axis. Similarly, on the positive side, the pink's going to start far because the blue starts close, going through our point and getting smooth. Sometimes that helps to see the graph on top as you draw it. Just make sure if you do put your graphs on top of each other, you clearly label which one is which by either using a different color or somehow marking the difference between the two graphs. Let's try one that's a little bit more involved. Let's graph f of x equals 1 over x cubed plus 3x squared minus 4. The denominator is a polynomial. We're going to have to use the rational root theorem to factor it because it's a cubic. Let's see. We could have 4 over 1, 2 over 1, or 1 over 1, plus or minus. And continuing on with the rational root theorem, let's try 1 first because it's the easiest to pull out. 1x cubed, 3x squared. Notice we're missing the 0x. And a negative 4. 1 comes down. 1 times 1 is 1. 3 and 1 is 4. Times 1 is 4. 0 and 1 is 4. Times 1 is 4. And 0. Hey, that did come out nicely. So we know we have a factor of x minus 1. What's left then is 1x squared plus 4x plus 4, and you should recognize that that is x plus 2 times x plus 2, or better said, x plus 2 squared. So fully factored using the rational root theorem to help us. So let's get rid of all this work here, just so that I have space to start making my graph. Remember, we are going to graph the denominator first, or the factored form that we just found, because it's going to be easiest. So just graphing the denominator over here. The zeros we see are at 1 and negative 2. If we plug 0 in for x, we find we have a y-intercept of negative 4. The negative 2 one was squared, so it's going to bounce at that one. So it's going to come in from the bottom left, bounce, go through, and up. That's our denominator. That's our x cubed plus 3x squared minus 4. Or if you prefer the factored form, x minus 1 times x plus 2 squared. Now we're going to try and graph the reciprocal. I'm going to graph it to the side first, and then I'll show you how we graph it on top in just a second. Some people prefer one method or the other. Key points. First key point that I see is the y-intercept at negative 4. It's now going to be at 1/4, bringing it down to the reciprocal. Next key points is we have 2 X intercepts. Those are zeros, and the reciprocal of 0 is infinity. So we're going to put a vertical asymptote at 1. And a vertical asymptote at negative 2. So now we've essentially split the graph into 2 parts. I'll even just do it both at the same time. Actually, let's do both graphs at the same time. Vertical asymptotes through the zeros. I don't know what's going on here. There we go. Maybe even delete that. The 4 became a 1/4. So we split the graph into 3 parts, the left, the middle, and the right. we're going to graph our reciprocal in the same way in 3 parts: the left, the middle, and the right. On the left side, notice we start next to infinity and go down to 0. All negative, all below the x-axis. So we're going to do the exact opposite, is we're going to start next to 0 and go to infinity, all negative. Seeing that on top of the graph, infinity starts next to 0 and goes to infinity, goes the opposite direction. Now in the middle, this is interesting. In the middle, it starts next to 0, goes to the key point, and goes back to 0. All negative. So we're going to do the opposite. We're going to go infinity to the key point to infinity. Again, all below the x-axis. So infinity, oops, let me change colors. Infinity up to the key point, and then back down to infinity. Negative. Seeing it on top of the graph, the 0 becomes a negative infinity, up to the key point, and back down the opposite direction. On the right side, the right side is now positive above the x-axis, so we're going to be positive above the x-axis also. It starts at 0 and just goes off to infinity. So we're going to do the opposite. We're going to start at infinity and go down to 0. Start at infinity and go down to 0. We've now graphed the reciprocal 1 over x cubed plus 3x squared minus 4 on our graphs. By identifying these key points of the denominator, we can generate the reciprocal function quite nicely, using the big little principle, doing the opposite of what the graph does. In fact, we don't even need a function to start with. We can start just given a graph and come up with the reciprocal of that graph. So let's make a graph here and see if we can find its reciprocal. Let's see. Let's do some key points at 0, 2. We'll do an X intercept here at -1. We're also going to do a key point here at 3, 1. And I'm going to put a vertical asymptote at 2. And I'm going to put a vertical asymptote at -1. So when I draw my graph in, we're going to start at 0, loop up to infinity, start at infinity, come through my points, down. And then this one's going to be a little different. I'm going to come up here. When I hit 3, 1, I'm going to bounce back up to infinity. We're going to attempt to graph the reciprocal of this function. And we should see the reciprocal of every key point work its way into this function. So there's really 5 key things in this graph we need to look at. First, the 3 points. The 0, 2 is going to become 0, 1/2, the reciprocal. The X Intercept again becomes a vertical asymptote. Three, 1 is going to become 3, the reciprocal of 1. Well, the reciprocal of 1 is 1 over 1, so we actually still have the point 3, 1 on this graph. So those 3 points became reciprocal points. 2 dropped down to a half. 1, the reciprocal of 1 is still 1. The 0 became a vertical asymptote. Which brings up the interesting point about the vertical asymptotes in the original graph. If the zeros become vertical asymptotes, then asymptotes should become zeros. We've actually got a 0 here at -1, and a 0 at 2. Now we're ready to connect the dots using the big little principle. On the left side of this asymptote, we go from 0 to infinity, which means our graph should do the same thing, but in reverse, go from infinity down to 0. And notice we do that going down to our point. Actually, I should probably put some curve to it, because after that 0, we're still positive, and we go from infinity down to 0, so we're going to do the same thing on our graph. We're going to loop up and go from 0 to infinity. Well, infinity is a vertical asymptote. Now what happens? We're going to go from 0 to negative infinity. We're going to do the opposite. Go from negative infinity to 0. Negative infinity up to 0. And then what happens? We go from positive infinity to our point, and then back up to positive infinity. Which means we're going to have to do the opposite. Go from 0 to our point, back to 0. 0 to our point. Whoops, let's do it in pink. 0 to our point, and then back to 0. So we get this little hump. Let's see it on top of the graph here. On top of the graph, on the left part, we went from 0 to infinity, all positive, so we'll go from infinity down to 0. Then we go from infinity through the Y-intercept at 1/2 up to a vertical asymptote. Then we go from 0 to negative infinity, so we do the opposite, go from negative infinity to 0. The graph goes from infinity to the point to infinity, so we go from 0 to the point to 0. And that is now our reciprocal graph 1 over f of x. In pink, 1 over f of x. So this is kind of the idea of working with a reciprocal function. Find our key points. We're especially interested in zeros and asymptotes. Then our graph should do the opposite. If we go from infinity to 0, go from 0 to infinity. Flip it over. Big little principle. Zeros become asymptotes. Asymptotes become 0. Take a look at the homework assignment. Practice these. It's a little awkward at first, but once you get the pattern to it, you'll be able to graph these reciprocals quite quickly, which will get us all set up and ready for graphing full rational functions tomorrow. We'll see you then. Section 3.5 takes a look at how we can graph rational functions. We've already graphed reciprocal functions, which are a special type of rational function. But when we're graphing rational functions, This means instead of graphing functions with something in the bottom, q of x, or whatever that was, like we did with reciprocals, and a 1 on top, now we're going to see a p of x, or a function in the numerator, as well. In this case, we're going to find some key info that's going to help us in order to graph the function. So 5 key pieces. First, we're going to want to know the x-intercepts. And the way we find an intercept is we make the other variable equal to 0. So we make y equal to 0. And then when we multiply by the denominator, what this really, in effect, will do is take the numerator and make the numerator equal to 0. And solve that function. And that'll give us the x-intercepts. The second thing we're going to find is the y-intercepts. And just like the x-intercept, we make the other variable equal to 0 and solve that to figure out what the y-intercept will be. The third thing we're going to look for are any undefined points. And undefined points can take one of 2 forms. If we can factor and divide out a factor, that means there's going to be a hole in the graph. In other words, if a graph would normally have looked like this, somewhere along the way at that point that divided out, there's going to be an actual hole in the graph, a gap in the graph. The other option is if it doesn't divide out, we look at what's left after the reducing, and we make the reduced denominator equal to 0. Because that's going to give us a vertical asymptote. Because the fraction can never have 0 in the denominator, it's going to give us an undefined point, which will either be a hole that divides out, or more often a vertical asymptote that the graph is going to grow closer and closer to. So those are our undefined points. The fourth thing we're going to find is any other asymptotes. And these other asymptotes can take one of 3 forms. One is if the degree of the numerator, actually let's start with the denominator. The degree of the denominator, because that's what we're really interested in, is greater than the degree of the numerator. In this case, if the degree of the denominator is bigger than the degree of the numerator, the denominator is going to be considered bigger, taking over, and we're dividing by a big, huge number, and so basically we'll get a horizontal asymptote at y equals 0. For example, we have x to the 5th over x to the 7th. That's going to reduce down. The denominator is going to take over. We're going to divide by a huge 7th power. It's going to give us 0 for the horizontal asymptote. Now, if the degree of the denominator is equal to the degree of the numerator, we will reduce leading terms. What I mean by that is if we have like 15x to the 7th over 3x to the 7th, and then there's 6, 5, 4, 3, 2, 1. But the leading terms were the x to the 7ths. Here we can reduce the x to the 7ths out, and 15 over 3 reduces down to 5. And so that is our horizontal asymptote. The other option we have is just the opposite. If the degree of the denominator is less than the degree of the numerator. Then we say that the asymptote is a curve. And I use the word curve lightly because it might be a straight line. It's just a diagonal line. And what we'll do in this case is we will use long division, or synthetic if we can, to find the slant asymptote. The last thing we're going to find about all these graphs in order to graph them is the positive and negative regions. And the way we find the positive and negative regions is we take this function p of x over q of x. That is our rational function. And we're going to write it as a product. We will write the p of x times the q of x. We will multiply the top and bottom together and graph this part. Because both graphs of the division and the product, both graphs have the same sign. Because if a positive is divided by a positive, it's the same as a positive multiplied by a positive. They're both positive. Positive divided by a negative is the same as a positive multiplied by a negative. They're both negative. They have the same sign. Now what's important to note about these two graphs is that they have no other connection. It's just easier to graph a product than to test quotient. So we'll graph the product just to see where is the graph positive and negative. And that's all we'll care about on that graph. Then we'll discard it, take that positive negative information and translate it onto our rational functions. So 5 things to find. You should know how to do all 5 of these before the test, preferably before you come to class today. The X intercepts, the Y intercepts, the undefined points, the other asymptotes, and the positive negative regions. We're going to do several examples where we're going to work through all 5 of these steps and see how they translate into graphs. So if f of x equals x minus 2 over x plus 2. First, we're going to find the X intercepts. To find the X intercepts, we make the numerator equal to 0. X minus 2 equals 0. And if we add 2 to both sides, we get x equals 2. There is the X intercept. The Y-intercept is we make the x's equal to 0. So we have 0 minus 2 over 0 plus 2 gives us negative 2 over 2, and so the y-intercept is at y equals negative 1. Next, we need to find the undefined points. The undefined points are when the denominator equals 0, and it's either a whole or a vertical asymptotes. This graph's not going to reduce at all. X minus 2 over x plus 2, that's not going to reduce. And so all we need to do is make the denominator equal to 0, subtract 2 from both sides, and x equals negative 2 is going to be a vertical asymptote. So to review what we've done so far, we made the numerator equal to 0 to find the x-intercepts. We plug 0 in for the x's to find the y-intercept. And we made the denominator equal to 0 to find the undefined points. To find the other asymptotes now, we take the leading coefficient of the numerator, which is x. I should say other asymptotes. The leading coefficient of the numerator, which is 1x, over the leading term of the denominator, which is 1x. Those both have the same degree on them, so that's going to reduce to 1 equals y. This is your horizontal asymptote. The last thing we have to find is the positive and negative regions. And to do that, we graph the product of the numerator, x minus 2, times the denominator, x minus 2 times x plus 2. And when we graph that, x minus 2, x plus 2 have intercepts at 2 and negative 2. The x squared, if we were to multiply those together, x squared would be positive, so it's a positive x squared, so it's going to come in from one side, come out the other side. This graph is going to have the same signs as our graph, so it's going to be positive on the left, positive on the right, and negative on the center. Better said, it's going to be positive from negative infinity up to negative 2. Union, it's going to be positive again from 2 to infinity. It's going to be negative in the middle from negative 2 to 2. So let's see if we can combine all this information together. I'm not going to be able to fit it on the same screen, so we're going to do a lot of scrolling. We're going to combine all this information together to make our graph. Okay. First, the x-intercept is at 2. So on the x-axis, we'll have a point at 2. The y-intercept is at negative 1. So on y, negative 1, we have an intercept. The undefined point is x equals negative 2. So at x equals negative 2, that was a vertical asymptote. Our other asymptote was at y equals 1. So when y is 1, there's our horizontal asymptote. And then we're ready to make our graph, knowing it should be positive to the left of 2. So to the left of 2, it's positive. From negative 2 to 2, it's going to be negative. From negative 2 to 2, it's going to be negative. And then from 2 on, it's going to be positive. So we know the graph is going to be positive on the left, and it's going to bend around those asymptotes. The only way to be positive on the left and bend around the asymptote is to be in the top left corner. After we cross that asymptote, we're going to be negative, and we have to go through the y-intercept and the x-intercept. And then notice we're going to go towards that asymptote staying positive. And we now have our graph of x minus 2 over x plus 2. Let's take a look at another example where we run through these 5 things. We're going to graph f of x equals x plus 3 over x squared minus x minus 2. First, we're going to find the x-intercepts. The way we find an x-intercept is we make the numerator equal to 0, x plus 3 equals 0. Subtract 3 from both sides, and x equals negative 3. Then we find the y-intercept. And the way we find the y-intercept is we make all the x's equal to 0. So we have 0 plus 3, which is 3. Y equals 3. Over 0 minus 2, which is negative 2. The y-intercept is at negative 3/2. Undefined points. To find our undefined points, first we'll need to factor that denominator. That denominator is, let's just rewrite it factored here, x plus 3 over x squared is x times x, 2 is 2 times 1, and that's negative 2 and a positive 1. There's no reducing of this fraction, so this fraction is going to have no holes in it, but we can make the denominator equal to 0. So that's x minus 2, x plus 1 equals 0. Add 2 to both sides, and x equals 2. Subtract 1 from both sides, and x equals negative 1. And those are both vertical asymptotes. This one's going to have 2 vertical asymptotes. I'm going to call it OA for other asymptotes. To find the other asymptotes, we take the leading coefficients, x in the numerator over x squared in the denominator. And because the x squared is bigger, here the degree of the denominator is bigger than the degree of the numerator, it's going to be dividing by a bigger and bigger thing. And when we divide by bigger things, we end up at y equals 0. If you divide by a lot, you're not going to have much left. Y equals 0 then is going to be our horizontal asymptote. Finally, the last thing to find is the positive and negative regions. Positive and negative regions are going to take the numerator times the denominator. In fact, we're going to take it in factored form because we've already found that. X plus 3, x minus 2, x plus 1. So we know the x-intercepts here are negative 3, 2, and negative 1. If we multiply this out, we've got x times x times x, which is a positive x cubed for the leading coefficients. So we know the shape is going to come up and out. Putting our intercepts at negative 3, 2, and negative 1. It's going to come up, bend, and up. Remember, x cubed, if it's positive, starts in the bottom left. And so what we find is the graph is positive from 0 to 2. Whoops, no it's not. Let me try again. The graph is negative from negative infinity to negative 2. Then it's positive from 2 to negative 1. Then it's negative from negative 1 to 2. And then it's positive from 2 to infinity. So again, it's positive from negative 3 to negative 1. Union, it's positive again from 2 to infinity. It's negative from negative infinity to negative 3. Union, it's negative again from negative 1 to 2. Our graph is going to follow that same pattern. So again, our 5 pieces of information, let's translate them onto a graph. Starting with our x-intercept, was at negative 3. Our y-intercept was at negative 3/2. So on the y, negative 3/2, right here. Our vertical asymptote, two of them at 2 and negative 1. So at 2 we have a vertical asymptote, and negative 1 we have a vertical asymptote. Horizontal asymptote is at 0. And then we've got our positive negative regions. So we said the graph is going to be negative from negative infinity to negative 3. Then it's going to be positive from negative 3 to negative 1. Then it was going to be negative from negative 1 to 2. And then positive from 2 to infinity. So our graph is going to follow that same pattern. Let's start on the right side, because this is probably easiest to start from the right side. This one's going to be probably easier to start on the right side and work our way over to see what's happening. On the right side, you see we have to be positive and approaching the asymptote. So it's pretty clear that we're going to have to be in that top right area. In the middle, we can see we're negative, and we have to go through that Y-intercept. We're also going to have to go towards the asymptotes. Notice we always stay negative, which means at some point we're going to have to bend back down and come back down negative. We can't keep going up. We can't become positive. Now the left side of this graph is particularly interesting because there's a horizontal asymptote, but we also have to go through it. So notice the graph has to start positive on the right side and go through that point. But now it's going to have to bend back and go towards that asymptote. So this graph is going to have some type of bend back to it to get it back to the asymptote, but always staying negative. So this now is the graph of x plus 3 over x squared minus x minus 2. Let's try another graph. Let's do the graph of f of x equals x squared minus x minus 6 over 2x squared minus x minus 3. Again, finding our 5 things. The x intercepts we find by making the numerator equal to 0. And if we factor that numerator, it's x minus 3, x plus 2 equals 0. So there's 2 x intercepts here at 3 and negative 2. The y-intercepts, we know we find the y-intercepts by putting 0 in for all the x's, which gives us negative 6 over 3, and that's going to reduce to negative 2. So the y-intercept is negative 2. Undefined points. Undefined points, we're first going to have to factor it to see if it reduces. That way we know what type of undefined points we're working with. So the numerator, we've already factored. It's x minus 3 and x plus 2. The denominator is going to factor to 2x and x. And we're going to need a 3 and a 1. If we do 3 and 1, negative 3 plus 1 would give us that negative 1 in the middle. It doesn't look like anything's going to reduce out here either. So, let's make them both vertical asymptotes. We make the denominator equal to 0. 2x minus 3 times x plus 1 equal to 0, which means x equals 3/2 and negative 1 when we add the 3 and divide by 2. The other asymptotes, we take those leading coefficients and reduce them, x squared over 2x squared. And the x squareds are going to reduce out here, leaving behind 1/2. So that's going to be our horizontal asymptote, 1/2. To figure out the positive and negative regions, we take the numerator times the denominator. Factored form is probably best. We'll do x minus 3, x plus 2, 2x minus 3, and x plus 1. And if we multiply x times 2x times x, we get 2x to the 4th, which means it's going to come in from a positive, wiggle, and go out from a positive. And those x-intercepts are 3, -2, 3/2, and -1. Just a quick sketch so we know what we're dealing with. 3, -2, 3/2, and -1. It's going to come in, bend, and out. 4th power, going up to the positives. So we see it's positive up till the point -2, then it's negative till -1, then it's positive till 3/2, then it's negative till 3, and then it's positive to infinity. So its positive range is -infinity to -2, union -1 to 3/2, union 3 to infinity. It's negative in between there, from -2 to -1, union from 3/2 to 3. We have our 5 pieces of information. We now should be able to make this graph. First, the x-intercepts were at -3, or I'm sorry, 3 and -2. So 3 and -2. The y-intercept, that one was at -2 on the y-axis. The undefined points, they're both vertical asymptotes at 3/2 and -1. So vertical asymptote at 3/2 and a vertical asymptote at -1. And then a horizontal asymptote at 1/2. Short horizontal asymptote there. And then the signs of our graph, we're going to be positive from -infinity to -2, and it makes sense when we go through the x-axis, we'll be negative from -2 to -1. Then from -1 to 3/2, we're supposed to be positive. Then from 3/2 to 3, we're going to be negative, and then positive again from there to infinity. Which makes me look at an interesting point here. Our y-intercept is -2. But yet we're supposed to be positive in this range. That's not going to work. So let's go back and check our work and see what happened there. Oh man, let's look at that y-intercept. Ah! Here's what happened with our y-intercept. There was a -3 in that denominator that didn't get copied down into our work. A negative divided by a negative is a +2. So yes, indeed, that y-intercept should be at a +2. So let's get him out of there and move him to a +2 like we expect. Now he's going to be positive in the middle, which we expect to happen. That matches. The y-intercept agrees with the positive negative regions. The nice part about doing all 5 parts is all your parts should agree with each other. Your positives and negatives should change at intercepts and asymptotes. Your y-intercept should agree with the positive negative regions. Sometimes students skip the positive negative regions and they miss errors they would have otherwise caught. So please take the time to find all 5 parts because it's really going to help you see what happened. So now as we fill in close to the asymptote, we start positive, go through the point to turn negative. It's the only way that would have made that graph work. Now starting with the asymptote, we come down, we're positive like we expect, go through the y-intercept, and then staying positive, so we have to go back up. And then finally the right side, close to the intercept, starting negative, and then turning positive, going towards that that horizontal asymptote. This is the graph of x squared minus x minus 6 over 2x squared minus x minus 3. All 5 parts. Filling in the blanks. Let's do another one. It's a little tricky trying to remember what parts we do. The whole key to learning this process is to practice, practice, practice. So you know what piece to go for, where to find it, and how to use it to make your graph. Practice, practice, practice. If f of x equals x squared minus x minus 2 over x plus 2, we're going to graph this. Starting with the x-intercepts. The x-intercepts come from when the numerator equals 0, so when we factor that numerator, it's x minus 2 times x plus 1. Make it equal to 0, and then it's clear that our x-intercepts are at 2 and negative 1. Y-intercepts, we get those by making all the x's equal to 0. This time we're going to be careful of our signs, giving us negative 2 over 2, which reduces to y equals negative 1 for the y-intercepts. The undefined points, we need to first factor that numerator so that we can see if it reduces, so we know what type of undefined points we're working with. We said it was x minus 2, x plus 1 over x plus 2. Nothing's going to reduce, so that denominator equal to 0 is going to be a vertical asymptote. So x equals negative 2 is a vertical asymptote. Other asymptotes? You'll notice on the other asymptotes, the exponent in the numerator, the x squared, is bigger than the x in the denominator. This means we're going to have some type of slanted or curved asymptote. And the only way to get it is to do the long division implied by the fraction. Now, fortunately, this fraction, the denominator is x plus 2, we can use synthetic division with negative 2 coming out. So negative 2, 1, negative 1, and negative 2. We're going to synthetically divide the denominator into the numerator. Gives us 1, negative 2, negative 3, 6, and 4. So it's going to be 1x minus 3 with a remainder of 4. With slant asymptotes, we don't care about the remainder. The remainder tells us we're getting closer to x minus 3, but we're not actually going to hit it. The actual function itself tells us the slant asymptote that this graph is approaching. Y equals 1x minus 3 is our slant asymptote. That means on the edges the graph is going to approach a diagonal line. Last thing to find then is the positive and negative regions. To do that, we make the numerator times the denominator using the factored form, x minus 2, x plus 1, x plus 2. So the x-intercepts are 2, negative 1, and negative 2.
Notice it's a cubic, 1, 2, 3 x's, and it's positive, so it's going to come in, wiggle, and go out. 2, -2, and -1. So it's going to come in from the bottom because it was positive, wiggle, and go out. And all we care about here is the sign. Negative on the left side, positive for a while, then it's negative for a while, and then it's positive till the end. So it's positive from -2, whoops, that's supposed to be -2, and +2. That's what I get for moving too fast. Let's get rid of a tick mark. Not the whole axis. Get rid of a tick mark. There we go. Now it's at 2. From -2 to -1, it's positive, and then union, it goes positive again from 2 to infinity. Negative is everywhere else, from -infinity to -2. Union, it's negative again from -1 to 2. Now we're ready to graph our function. Starting with the X-Intercept, which we said we're at 2 and -1. 2 and -1. The Y-Intercept's at -1. So -1 for the Y-Intercept. Undefined, we have a vertical asymptote at x equals -2. We have a slant asymptote at y equals x minus 3. We should know that has a y-intercept of -3 and a slope of rise 1, run 1. So if we make a couple dots to give us an idea of where this graph is going. There's our slant asymptote. So we might need to extend a few lines just in case here. Okay. Then our positive negative regions, it's negative from -infinity to -2. Then it's positive from -2 to 1, -1. Then it's negative from there till 2, and then it's positive from there till forever. Let's do the middle first here. We can see the middle of the graph, we're close to the horizontal asymptote. We go through our points, and then it has to start going close to that asymptote. Notice that perfectly follows the asymptotes. It perfectly follows the positive negatives. It also goes through all the points. That matches everything. On the left side of the asymptote, though, we have to be negative the whole time. So if we're going to start close to the asymptote and be negative, we're actually going to be down here, and then we have to bend and go towards the slant asymptote. So this one has its slanted part down below. So all that together becomes the graph of x squared minus x minus 2 over x plus 2. I have one last example I want to do then. F of x equals x squared minus x minus 6 over x minus 3. And in fact, you know we're going to have to factor everything. And so what a lot of people start doing is they start factoring at the beginning rather than halfway through and doing it halfway. So let's factor it. It's going to factor to x times x, and to get -6, it's going to be -3 and +2. So we've got an x minus 3 in the denominator.
And one thing you probably notice is those x minus 3's are going to divide out. That's going to be significant to us here in a minute. So when we're finding our x-intercepts, those points that have divided out really aren't going to be a part of it. So while we make the numerator equal to 0, we only have to take what's left to equal 0, which is nice. X plus 2 equals 0. And so when we subtract 2, we get x equals negative 2 for our x-intercepts. Our y-intercept, again, we only need to take what's left and plug 0 in there. So we have 0 plus 2, or y equals 2, for our y-intercept. Our undefined points are when the denominator equals 0. But notice, after we reduce, there's nothing left in the denominator. This means we don't have any vertical asymptotes. However, we still have an undefined point. This is the piece we don't use very often, going all the way back to the beginning, but when we do, it becomes important. If we can divide out something, we get a hole in the graph. So down where we are, that x minus 3 that divided out, if I can get the right color, that x minus 3 that divided out, solving that gives us x equals 3. That isn't a vertical asymptote. That is a hole in the graph. We'll talk about what that looks like in a minute. Other asymptotes? Well, after we reduced, all that was left was the x plus 2. There's really no division to do. Really, it's just approaching the line y equals x plus 2. In fact, we're going to find something very interesting about that line y equals x plus 2 here in a minute. In terms of our positive and negative regions, graphing what's left after we reduce x plus 2 gives us just 1, 0 at negative 2. In fact, we know that x plus 2 graphs as a straight line. And so it's going to be negative on the left and positive on the right. It's going to be positive from negative 2 to infinity. It's going to be negative from negative infinity to negative 2. So let's put this information on the graph. The y-intercept, the x-intercept is at negative 2. Let's start there. The y-intercept, I think, was at positive 2. Yep. There's a hole in the graph at x equals 3. The way we're going to find where that hole is we're going to plug that 3 into the remaining stuff. 3 plus 2? 3 plus 2 is 5. So 3 comma 5, there's going to be a hole in the graph. So at 3 comma 5, there's a hole in the graph, and it should be orange. I'm using the wrong color. In terms of asymptotes, it's going to be getting really close to x plus 2, but what you actually see is this graph is following actually the line x plus 2. The asymptote is the graph. In fact, this is just a straight line with a hole at 3, 5. But that kind of makes sense, because this whole time we were making our graph, we said we were going to focus on the part that was left after we reduced. What was left after we reduced was x plus 2, and so what's left in our graph is the line x plus 2. We just have to account for the hole that we divided out.
So that's how we graph these rational functions. We find these 5 important pieces of information. First, we find the x-intercepts by making y equal to 0, or essentially the numerator equal to 0. Then we find the y-intercepts by making all the x's equal to 0. Then we find our undefined points. Generally, that's going to be a vertical asymptote, but sometimes it's a hole in the graph. Find our other asymptotes. It's going to be a horizontal asymptote if the denominator is greater than or equal to the numerator in terms of degree. We either reduce or end up with a 0. But in the rare event that the denominator has a smaller degree than the numerator, we have to use long division in order to find that curve that it's going to get close to. And finally, we found the positive and negative regions, and that helped us identify the signs of our rational function. These are going to take practice to get all 5 of these processes down, knowing what to find, where to find it, and how to use it. Once you get a good practice with that, you'll be ready to go. So we will see you in class tomorrow.